Okay, now consider another problem. I will return to the problem which we considered in the first lecture. It is air pressure. So consider the pressure of the air in the atmosphere as a function of vertical coordinate z. So the function pressure as a function of z. As I explained first, why we have the air pressure, because the air is compressed by the weight of the air above the point of measurement. So if you measure it at the ground level, we have the whole atmosphere, divided it, its weight by the take it as per 1 meter, 1 square meter, yes. So we consider the column of air, it is 1 square meter, yes, and the pressure of air at some coordinate z, at some height z, is equal to the weight of the air above this point. So it is material cause of the air pressure. So now it is clear that the higher we go up, the less is this weight of the air. So it is decreasing, eventually going to zero. We know that if you go to the space, then the air pressure there is very close to zero. The pressure is described by the following equation. dP dz equals minus G times rho of Z. It is pressure, and rho of Z, it is density. I mean air pressure and air density. Now we have a new unknown function rho, and this function rho depends the density. Of course, it depends on the pressure, air pressure, but it depends on something else. It depends on the temperature. Yes. Now we can express it in the following form. P depends on rho and the temperature, T, absolute temperature. So T equals theta plus 273.16 and so on. So this is the temperature, if you take minus, is the temperature of absolute zero. Yeah. So let us measure the temperature in as absolute. So it is measured not in degrees of, say, Celsius or Fahrenheit, but in kelvins. No, Kelvin is approximately like degree of Celsius. Okay, and so for our air, it is a, so P is a function of rho and T. This function has the following form. P equals alpha rho divided by T. No, it is P alpha rho multiplied by T. So here we have, it is it is combined Charles and Boyle-Mariotte law. So Charles is that pressure is proportional to absolute temperature, and Boyle-Mariotte that for a constant absolute temperature it is proportional to density. Yes? So here we have this. Now from this equation, and now we can write that rho, to substitute here, equals P divided by alpha T. Now here, rho is a function of z, P is a function of z, and in general T is a function of z. Yeah? So your rho of z equals P of z divided by alpha temperature of z. Now, what we did in the first lecture, we considered the case when temperature in fact is constant. It is the same, equal to temperature at the ground level. And today I wanted to consider the case when temperature is not constant. We know that in general temperature is going down, and the height which we are interested in, interesting range of the height is about 10 kilometers. This is the height where the jet planes are flying. Yes, so the question is, what is the air pressure at the height 10 kilometers? Yeah. So what we know if they take the typical figures, if at the height, at the ground level, so we take T of 0 equals, say, T0 is, let's say, take 20 degrees plus 20 degrees plus 273, let's forget about this, 293 kelvins. Yes? And T at the height 10 to the fourth meter, 10,000 meters, is, say, equal to minus, no, typically 50 degrees Celsius equals, so minus 50 plus 273 to 23 Kelvin. Yeah? So we have 2 points. And it is Z, it is T, it is temperature at ground 0, it is T0, it is the temperature at the, say, equals T of Z1. Z1. Here is this equals T1. So this is T1. And here is some curve. No, the first approximation, it is already second approximation. We approximated by linear function. Yes? So we have T of Z equals T0 minus beta Z. So what is beta? Beta is a coefficient which is beta equals T0 minus T1 divided by Z1. Yeah, it is, so if you substitute here, if you multiply it, find T of Z1, it is T0 plus minus T0 plus T1. Yes, it is correct. So we have no the approximation of linear temperature. So temperature decreases as a linear function. And so our equation is dP dz equals minus G alpha T of Z P. And T of Z is here. So dP dz equals minus G divided alpha T0 minus beta Z E. No, this is also a linear equation, but it is even simpler. It is linear homogeneous equation, or maybe equation, it is separable equation. So let us solve it as a separable equation. So dP divided by dP divided by P equals minus G divided by alpha T0 minus beta Z yes. So integral dP divided by P equals minus integral g alpha t0 minus beta z dz, no, plus c. We find this c later. Logarithm p equals minus integral g divided by alpha t0 minus beta z dz plus c. Now we have to find this integral. To find this integral, we assume that beta is not 0. Beta is different from 0. So, integral g divided by alpha t0 minus beta z dz equal, let us put this constant g divided by alpha and divided also, let us divide by beta, g divided by alpha beta integral dz divided by t0 divided by beta minus z plus c. Yeah? Now let us write it what it is. Now we will return to this constants and so on. Equals to what? G alpha beta logarithm model, but you see, if 0 equals z equals 0, then the denominator is positive, and we have to move in the domain where it is possible, positive, yes? This means that what is here, it is the temperature on the height. So I assume that the temperature is always more than absolute 0. Yeah, otherwise it makes no sense. So this means that logarithm of positive number t0 divided by beta minus z. And so we have logarithm p equals minus, here is minus, g over alpha beta logarithm t0 beta minus z plus c. P, let us now take exponent of left and right hand side. P equals e to the power c times e minus logarithm e minus something now logarithm. It means that t0 divided by beta minus z to the power minus g divided by alpha beta. You should be careful with this integral no, let us denote this equals C1 T0 beta minus Z the power minus G alpha beta. Now to solve the equation we should find C1. We have the initial condition that C1 that at the ground level it is given, so we can measure the temperature at the ground level, we can measure the pressure and measure the density. So we write P of 0 equals C1 C0 divided by beta Z minus G divided by alpha beta. Now we have to say equals P0. Yes, so C1 equals P0 T0 divided by beta, the power G divided by alpha beta. Okay, now we have to say something about alpha and beta. Beta equals it is the gradient of temperature. It is T0 minus T1 divided by Z1 equals, so here it is 293, there at Z1 it is 223, so the difference is 70 degrees, and so it is 70 divided by 10 to the 4. It is beta. Now, about alpha. So, rho of 0 equals 1.2 kilogram or per meter cube, yeah. P of 0 equals, no, approximately 10 to the 5 Newton per meter square. Now, what else? T of 0 equals 293 Kelvin. And so now let us recall the equation of gas state. The pressure equals alpha, temperature, rho. Alpha equals pressure. In particular, it holds at z equals 0. So T0 is P0 equals alpha T0 rho 0. Alpha equals T0 rho 0 divided by P0. So here the answer for alpha 284.4. If I take these values of rho bt at 0, and beta is 0.007. Is measured in Kelvin per minute. So for every meter higher, the temperature decreases by 0.007 Kelvin. Okay, so we have here alpha, beta, we have alpha, beta, and that's it. P0, T0. It remains to find the C1. Yes. Now let us transform a little this formula. Here beta is a constant. We found this constant. T0 is a constant, so let us divide by this constant, and we say P of Z is some other constant C3 1 minus beta divided by T0 Z to the power G divided by alpha beta. We can write in this form because anyway we have to, it is simply other constant. And in this form it is easy to find what is C3. If Z equals 0, this is 0, so this is 1. So C3 is P0. C3, so P of 0, if you substitute, equals C3. Yes? So it is P0. And finally we find the formula. P of Z equals P0 1 minus beta Tz T0 to the power G divided by alpha beta. Phew. So here alpha is here, beta is 0.007, and G approximately 10 meter per square second square. And so P of Z, so let us find P of 10 to the power 4 equals P0. P0 is about P0 is 10 to 5, yeah? 10 to the 5, 1 minus beta 0.007 divided by T0 to 93 to the power 10 divided by alpha 284 times 0.007, yeah? No, equals, no, it is P0. Let us find this. No, okay, taking our calculator and performing this operation, you have simply 0 to 54 P0. So if you have, say, 1 atmosphere or 1 bar, it was the pressure at the ground level, then at the height 10 kilometers, you have just 25% of it. Now, if we return to what was in our previous time we considered the case when the temperature was constant. Yes. So if the temperature is constant, it corresponds formally to beta equals 0. Yes. But then you have a strange thing. Here in the exponent, beta is in denominator. Yes, so this answer does not work. So we have to briefly solve this problem anew. So problem, if T of Z is constant, like T0. So then equation is the following. dP dZ equals minus G rho equals minus G divided by alpha P. Alpha T0 P. Yeah. So in this case, P equals alpha T rho equals alpha T0 rho, because T equals T0. So we have this equation, and P of Z equals P0 E minus G alpha T0 P, alpha T0 Z. Yeah, so this solution of this equation. And if you substitute here our figures, we have p of 10 to the 4 equals p0 e minus 10 divided by alpha to 84 and 4 times T0 293 times Z is 10 to the 4. No, okay. It is again exercise for calculator. So it is P of 10 to the 4 equals 0, 3, 0, 1, P0. So what we see in our first approximation, when we started solving this problem, we assumed that there was very coarse hypothesis that the temperature is constant all over, yes, and equal to the temperature on the ground level. And then you find that at the height 10 kilometers, the pressure is just 30% of pressure on the ground. And if you take into account that the temperature is decreasing, no, we take this linear decrease, no, it is just a model. We can modify it if you have more data. For now I have, at this moment I have just 2 points. I drew a line. So for non-isothermic atmosphere, which is closer to reality, we have that the temperature becomes 25%. So the error is just 5% in our forecast. No, it is not bad for applied problems with such primitive hypotheses and primitive tools. It is very good. I spent some time solving different applied problems, and in my experience it's not so bad. So I congratulate you with the first more or less realistic problem. And next we consider other circle of problems.